All right, so here we go. The first thing we're going to go over is we've been dealing with systems of equations, right? Which is more than one equation, right? And we're trying to find common solutions for more than one equation. And the other day we went over how to do it graphically. Today I'm going to give you a sample of substitution. And this is just is like an addendum to the Edpuzzle we did, so that you have something you can go back to and look at without having to go through the entire Edpuzzle again. So first we'll do a substitution problem, then we'll do an elimination, then we'll do a word problem, just to have clear examples of what those might look like. So say I have an equation that is x minus y equals -9 and 8x minus 3y equals -62. I didn't do this one yesterday. I did another one, but I like this one because the first step, if you remember from the Edpuzzle, is that I have to solve one of these for a variable, right? I either want to solve them for x or y. And you're always going to pick one that doesn't have a coefficient, or I should say has a coefficient of 1, right? We don't write 1 when it's the coefficient. So I'm going to go ahead and I'm going to solve this equation here for x. I could solve it for y if I want, but y is negative. And so I'm going to solve it for x because it saves me a step. So if I have x minus y equals -9, and I want to solve it for x, I just want x to be alone on this side of the equal sign. So I'm just going to add y to both sides, and I get the equation x equals y minus 9. Now, the cool thing about having x equals y minus 9 is anywhere that I have an x, I can just plug in y minus 9, because if they're equal, they're interchangeable, right? So I'm going to take this y minus 9 here, and I'm going to plug it in for y in this equation and try and figure out, and it's going to pull out one of my variables. So if I write in 8x minus 3y, well, we just know, oh, sorry, I'm going to plug it in for x. I've been doing a y problem all week, and I changed it for you. I'm going to take it, it equals x, so I'm going to plug it into x, not y. My bad. So I have 8x, right? Well, what do I know about x? I know it equals y minus 9. So I can just put in y minus 9 wherever there's an x. Minus 3y equals -62. Notice I no longer have an x in here, right? I only have one variable now. So I can just solve this for y. Now I have to start by distributing, and I get 8y minus, what is that, 72, minus 3y equals -62. Now I can combine my y terms, right? Combine our like terms, and I'm going to get 5y, 8y minus 3y is 5y, minus 72 equals -62. I'm just going to scooch this up a little bit so you can see the whole problem there. Now we're going to try and get everything off of this y, right? We're going to solve for the variable y. So we want y to be the only thing left on that side of the equation. So we're going to start undoing everything that's being done to it. So I'm going to start by adding 72 to both sides to get rid of that 72 that's on there. And I'm going to be left with 5y equals 10, right? Minus 62 plus 72 is just 10. I still have this 5 that's being multiplied to y, so I'm going to divide by 5 because that is the opposite of multiplication, and I get y equals 2. So I know part of that intersection now, right? I know what my y variable is, but I don't know what my x variable is. But I do know that y equals 2. If I was writing it in the form of a point, I don't know what x is yet, but I know that y is 2. So I can take this y equals 2 and I can plug it in to the original equation, right? So what's my original equation? I have x minus y. Well, what do we know y to be? 2 equals negative 9. And this becomes an easy solve, right? I just add 2, I add 2 to both sides, and I get x equals negative 7. So I can plug that in here as my point, or I could write x equals negative 7. Either way is fine to input it. I think on Delta Math, you need to input it as a point. So you're going to want to do it that way. The cool thing about systems of equations is you can always check and see if you're right. Like we know on this one, the first equation, that we're right because we used it to find the solution. But we could also go, well, 8x, well, that's negative 7, minus 3y, well, that's 2, equals negative 62. So if I do all the math on this and it equals negative 62, we know we're right. Both equations should be true. 8 times negative 7, I believe, is negative 56. Minus 6 equals negative 62. And that is true. Negative 62 does equal negative 62. So I can actually check and see if my solutions are right. I am not going to force you to do it. I'm not going to make you verify it, but you can if you want. And if you're taking a test, it's good to know that you can go back and check and see if your solution is right just by plugging it into the equations and seeing if you get a true statement. So that is substitution. We call it substitution because we substitute something in. Math is like that. Slope-intercept form is called slope-intercept form because it has a slope and an intercept. Point-slope form is called point-slope form because it uses a point and a slope. Substitution uses substitution. So elimination, what we're about to talk about, clearly we're going to be eliminating something, right? So the elimination method is a little bit more complicated in some ways. But if you don't have a variable without a coefficient or without a coefficient of 1, it's so much easier to do the math by just using elimination, because otherwise you're winding up dealing with a lot of fractions or square roots and stuff like that. So if you want to keep it to whole numbers, sometimes elimination is the better method. Now, I can't watch you do your homework because we are virtual. So, I mean, even if it says use substitution and you prefer elimination, as long as you get the right answer, it makes no difference to me. Either way, you should get the same solution. So I have this crazy problem right here, right? The idea is that I want to try and add these two equations together and get rid of one of the variables. So I have to create an opposite in one of the equations so that when I add the equations together, whether it be the x values or the y values, that one of the variables will drop out. What I mean by that is if I were to draw a line under here and I were to add these together right now, I'd have 2x plus 6x equals 8x, right? I'd have minus 9y minus 2y equals minus 11y. And here I get 26 minus 22 equals 4. I would like for when I add them together to have one of the variables drop out. One of the things that I can do to change an equation without changing the graph of that equation is to multiply it by something, because multiples graph right on top of each other. If you remember, I talked about that with the graphs the last time, which means I can multiply any equation times anything I want, and I'm not going to be changing the graph or solution set of that equation. So I'm going to look at this and I'm going to go, well, is there anything I can multiply 2 by to get -6, right? Because I want the opposite of this. Is there anything that I can multiply 2 by to get 6? That is a legit question I am posing to you people right now. Yeah, I could multiply it times -3 would be my better bet because I want it to be an opposite at the end. But yeah, 3 times 2 equals 6. So I'm just going to multiply by -3 just so I get an opposite. I'm going to go ahead and distribute this. -3 times 2x gives me -6x. -3 times -29 times -9y gives me positive, because they're both negative, 27y. And then -3 times 26, let's see, 25 times 3 is 75, plus 3 gives me -78. Now, I didn't do anything to this bottom equation. I'm just going to leave it as it is, but I'm going to rewrite it under here just so I have it all lined up. Now, I can go ahead and I can add these problems together, right? And the whole reason for doing this is this first part right here. -6 plus -6x plus 6x just equals 0, right? And so we've eliminated the x variable. And I'm going to get 27y minus 2y gives me 25y. Minus 78 minus 22 is -100, which is very convenient because 25 will divide evenly into that. To solve for y, I just have to divide by 25, right? We have 25 multiplied to it, so I can just divide by 25 and divide by 25, and I get y equals -4, right? So I know my first part of the point, right? It's -4 where the y would be. So I can go ahead and plug that into either one of the original equations and figure out what my x is. I'm going to do it to this one for no particular reason, just that nothing else has been done to it. So I've got 6x, still don't know what x is, right? Minus 2y. Well, minus 2, we know that y is -4. So where the y is, I'm just going to plug in -4 equals -22. And now I can just do the math and figure out what my x is. 6x plus 8, right? -2 times -4 is 8 equals -22. I'm going to subtract 8. I'm going to start undoing what's being done to that x. And I get 6x equals -30. I still have 6 being multiplied times x, so I'm going to divide by 6 and divide by, well, I don't know why I wanted to write -6 there. I get x equals -5. That is all I need to do. I have my solution set. I know that these 2 points on a graph would intersect at -5, -4. I could plug them into the other equation and see if they're true. I can tell you right now they are true, though, because this is the 6th time I've done this week so far. So I'm pretty good at this problem now. But that's basically how elimination works. The word problem I've chosen to do for you, I chose specifically because it shows us having to adjust both equations for the elimination piece. What I'm going to do, though, is I'm not going to write out the entire question. I'm going to read it to you once, and then I'm going to read it to you again and pull the math out as I read it to show you how to set up these word problems. Word problems where systems of equations are concerned are always fairly consistent in how they set up. So when you get to those context problems in your homework, you'll have a good example of how to set them up. I put one in the Edpuzzle as well. So I'm going to read the question. And it says, at the fast food restaurant, 4 cheeseburgers and 5 small fries have a total of 2,310 calories. 3 cheeseburgers and 2 small fries have a total of 1,330 calories. How many calories does each item contain? So the first thing you look for when reading one of these is, what do they want? And what they want is, they want to know, I don't know why every time I write the letter C, it wants to turn it into an O. They want to know calories in a cheeseburger, right? 1 cheeseburger. And they want to know calories in a fry, right? Well, 1 calories in small fry. Those are the pieces of information that they want to get from whatever we create here. So let's look at it again. It says, at the fast food restaurant, we've got 4 cheeseburgers and 5 small fries. So let's call those 4C and 5F, right? And they're saying that they equal together 2,310 calories. So they're saying 4 cheeseburgers plus 5 fries equals 2,310 calories, right? We have an equation there. The next piece of information it gives us says 3 cheeseburgers and 2 small fries. So we've got a 3C and 2F is 1,330 calories. So if we wrote that in the equation, it's saying that 3 cheeseburgers and is a plus, 2 fries equals 1,330 calories. What we have here is a system of equations. If we find out what 1C is, it will tell us how many calories are in a cheeseburger. If we find out what F equals, it will tell us how many calories are in a small French fry. But if I look at these equations that I have set up, I can't multiply 3 times anything to get 4, and I can't multiply 2 times anything to get 5. So I'm going to look at my bigger coefficient, and I'm going to go, well, what if I multiply 4 times 2? 4 times 2 gives me 8. Does 3 go into 8? Exactly. No, I could hear you thinking it. Even if you didn't tell me, I knew you were thinking it. But if I multiply 5 times 2, that's 10. Does 2 go into 10? Does anything times 2 equal 10? 5, right? If I multiply it times 5. So what I'm going to do is I'm going to turn this into a 10 by multiplying this equation by -2. And I am going to turn this into a -10. Well, I turned that one into a -10. So I'm just going to multiply this one times 2. Doesn't matter, right? As long as one of them is negative so that they're opposite. Oh, sorry, this would be 5, right? 2 times 5. Have an eraser on here. There we go. So here I have to multiply times -2 to get -10. Here I'm going to multiply times 5 to get +10. And then I'm just going to distribute. I have -2 times 4 gives me -8C. And then I've got -2 times 5 gives me -10F. And then I've got -2 times 2310 gives me -4620. So we've taken care of that -2 distribution. Now I have to do this one times 5. So 5 times 3C gives me 15C. 5 times 2F gives me +10F. 5 times 1330 gives me a calculator. 1330 times 5 equals 6650. And now I'm in a position where when I add these equations together, the F's are going to disappear, right? And we'll be able to solve for C, which is the whole point. So here I have minus 8C plus 15C. Well, that's going to give me 7C. These cross out. It's the whole reason we did the math. This is going to give me 2030. And when I divide both sides by 7 to figure out what C is, because I've done this one, I remember that it equals 290. So far I've learned that a cheeseburger, one cheeseburger, has 290 calories, right? What I still need to know is how many calories are there in a French fry. But I have these equations right here, right? I have 4C plus 5F equals 2310. And I have 3C plus 2F equals 1330. So I can plug this 290 into either of these for C, and I'll find out what the fries are. I'm going to do the bottom equation just because the numbers are smaller. So I've got 3C. But what do we know about C is that it is 290 plus 2F, which we don't know yet, we still need to figure out, equals 1330. And when I solve for this F, I'm going to know how many calories are in a small French fry. Now, 290 times 3 is 870, right? Plus 2F equals 1330. So I'm going to start by subtracting off, right? We're going to try and get this F by itself. So the first thing we need to do is subtract this 870 minus 870. I don't know what 1330 minus 870 is off the top of my head. And I get 2F equals 460. But I don't care what 2F is. I care what F is. So I'm going to divide both sides by 2 to find out what one French fry is, right? And I'm going to be left with F equals 230 calories. So what we learned is that there are 230 calories in a small French fry, and there are 290 calories in a cheeseburger. And that's how you're going to set up the word problems when we're dealing with systems of equations. Now, I'm not going to give you a 3-variable word problem. I will stick to 2 variables for the word problems. But definitely practice this. There's another practice problem in the Edpuzzle before you get to your Delta Math assignment. I'm going to just stop the recording and then I'll ask you guys for questions.